So the past two classes we're going over word and skeleton equations, and we're building upon this to balance equations. When you're balancing equations, you're going to be using a chemical reaction and basically figuring out the coefficients that you need. But to back up there, when you're balancing equations, first part is to identify the reactants and the products. So, and to do that, most of the time they put the reactants first, and then sometimes, and then the products second. But sometimes they'll flip them. And to understand the difference, you kind of got to read the whole thing. You got to read the whole problem as a whole and really think about what is happening here. There can be some key phrases, like when you see reacts with, that's a good sign that they're putting the reactants first, right? Barium chloride reacts with, so that must mean barium chloride is a reactant. And what it's reacting with is potassium sulfate. So those would be our two reactants. So barium chloride plus, and then potassium sulfate. Okay, and then a very kind of a common thing you'll see is the transition from reactants to products can be symbolized by that comma. Sometimes they'll say to produce, other times it'll just be a comma that is separating the reactants from the product. So here that comma would function like our reaction arrow. So then coming after the comma would be our products. So our first product would be barium sulfate. That's out. It looks so good from my vantage point. All right, barium sulfate and potassium chloride. Remember, you don't need to write the states of matter when you're putting these in. It isn't technically wrong to include the states of matter, but the point of the word equation is just to organize our thoughts. It's not really, you don't have to get as detailed with those. So for the sake of our formative, just go ahead and leave off the states of matter. So you have barium sulfate and then potassium chloride, and those are our products. And I think that isn't really what people are having an issue with. The issue is getting into the skeleton equation. So then that's because that's where we have to use the naming rules. So barium chloride, barium is a +2 charge. Chloride is a -1. Chlorine's a -1. Charge has got to get to 0, so that's why it's BaCl2. Okay? And then adding that to potassium sulfate. So that would be K for potassium. Thank you. And then sulfate's one of our polyatomic ions. Potassium got +1. Sulfate is SO4, and it has a -2 charge. So to get our charges to go to 0, we would need 2 potassium. So it would be K2SO4. And what am I forgetting to do? What's that? State of matter. As you can see, I almost forgot to do it. So it's a very common thing, but you have to include the state of matter. So if they say dissolved, well, what is barium chloride dissolved in? Water. That's what we're dissolving in. Something dissolved in water is AQ. Also, solution of would mean AQ. AQ stands for aqueous. And they tell us that potassium sulfate is also dissolved. So you would say AQ for that as well. All right, jumping into our products, you have barium sulfate. So barium is a +2 charge. Sulfate is SO4 with a -2. Because those charges already cancel out to 0, you can just leave it BaSO4. And they're saying it is a precipitate. So a precipitate is a solid. Anytime you see precipitate, that is a solid. Okay. And then plus potassium chloride. Potassium is K. That's got a +1 charge. Chlorine is a -1. So it's just KCl. And they say it's aqueous, so that would be dissolved in water. So there you go. Any questions about this? Okay, so getting into the new stuff, looking at our balancing equations. All right, so the basic idea of balancing equations is the law of conservation of mass. The law of conservation of mass is why we have to balance equations. And the law of conservation of mass says mass cannot be created or destroyed. In other words, what goes in must come out. And that's an idea you should have heard at some point throughout your science career, right? And here's the idea. Let's say I have a reaction where I have 100 grams of mercuric oxide, okay? The products I create are mercury and oxygen. If I start with 100 grams of this, in other words, if I have 100 grams in my reactants on the left side of the arrow, I must have 100 grams of products on the right side. That doesn't mean each individual product is 100 grams, but the combination of products would add up to 100 grams. Make sense? So that's the idea there. That's why we can balance equations. All right, so how we would balance equations, I'm going to show you kind of like maybe a good starting place to do it with. And this is even really how I do it. Some of these you can get a little bit quicker with, but I think a best bet to make sure you always get them right is they show you equations. So here you got methane plus chlorine gives you carbon tetrachloride plus hydrochloric acid. And to balance the equation, you need to have the same number of atoms on the left-hand side of the equation in our reactants as you do in the products. So if we look at this, we want to count our atoms. So on the left-hand side of the equation, how many carbons do we have? It'd be one, right? There's only one carbon there. And on the right-hand side, how many carbons do we have? It's one, all right? So our carbons, we would say, are balanced. Okay, we're good on carbons. If we look at our hydrogens, I have 4 hydrogens in my reactants, but only 1 hydrogen in the products. So we know we need to balance out our hydrogens. Now let's go with our chlorines. We have 2 chlorines in our reactants, and then only 1 chlorine in our products. So looking at how to balance the equation, this is where I was saying it can be kind of tough because there isn't. I'll show you some tips on how you, maybe some good rules to follow, I guess you could say, on how to balance them. But there's kind of a sense where you just got to play around with it to see how to balance it. I like to kind of go in order here. So if I see 4 hydrogens here, 4 hydrogens here, yeah, a minute.
Why is it 1 chloride?
Oh, I'm sorry. We have 5. Thank you for correcting that. My fault. Yeah, you got 4 chlorines here, and then 1 there. Yes, it'd be 5. Okay. All right. If you see something like a 2 and a 5, where there's not 2 doesn't go into 5, 5 isn't divisible by 2. That would be but 4 is divisible by 1. That's a sign we should tackle the hydrogens first, and we'll deal with the chlorines later. How you would tackle the hydrogens is I need to get that number to be 4. So what I'll do is I'm going to multiply my HCl by 4. What that's saying is when I'm doing this reaction, I'm going to produce 4 individual HCl's. So now you have to update your numbers in your products. Because I multiply this by 4, I now have 4 hydrogens, but that 4 also goes to the chlorine. So how many chlorines would I have now? What is it? 8, yeah, good, 8. So then I have 8 chlorines. All right, so then now we go back to our reactants. I need to get this number to be an 8. What do you think? How would I get that to be an 8? Thoughts? All right, good. Yeah, if I multiply this by 4, 4 times 2 would be 8. And there you go. They're balanced. So some problems are a little more complicated than that. It takes a little more, you kind of got to play around with it to figure it out. But that's the basic idea. And you would say that's a balanced equation. Now understand what this means. What this is saying is, in this chemical reaction, think of it like you're making a sandwich. We said you need 2 slices of bread for every 1 sandwich you make. This is saying you need 1 molecule of methane, or think of it like a recipe. If you're making a cake, it's like you need 1 cup of sugar and whatever else, like it doesn't mean you have 1 cup of literally every ingredient that you need to make a cake. There's different measurements of the ingredients. This is a similar idea. You need 1 methane plus 4 chlorine molecules to make 1 CCl4 and 4 HCl's. That's the ratio of the different things you have in this reaction. Haley? Yeah.
What did you say about starting with hydrogen?
Oh, I was saying we started with the hydrogens because it was actually divisible by, because we had 5 chlorines on the left side and 2 on the right side. So sometimes, like here, what would end up happening is if you tried to balance the chlorines first, there's no number you can multiply HCl by to get you to 5 chlorines. Well, I guess you can multiply by 5, but then sometimes I can mess up the numbers on the other side. It's possible to try doing this a different way, but I'll show you some different rules that can kind of help you out. There's different ways to do this. It's just some ways it might take you a little bit longer. I think this is one of those things, the best way is just to keep doing sample problems. It's kind of hard to explain all of it just through one sample problem, if that makes sense. So let's kind of look at some other ones. So here's kind of some general tips, some general rules that you'd want to follow. One isn't really a tip, it's just something to keep note of. If there is no number in front of a molecule, that means there's 1. In other words, if you see O2 in a reaction, you assume there's a 1 in front of there. You assume this only means 2 oxygens. Okay? And the numbers in front, they're actually measures of moles. This we'll use later on in the next unit. We're going to do something called stoichiometry. This will make a little more sense, what they mean by moles and stuff. But the other is the coefficient in front multiplies across all the subscripts in the compound. Meaning, if you put a 2 in front of H2O, you now have 4 H's and 2 O's. And again, when we say 4 H, it's technically referring to 4 moles of hydrogen atoms and 2 moles of oxygen atoms. A mole was Avogadro's number, 6.022 times 10 to the 23rd. So that's what we're actually talking about. This will make more sense next unit when we start doing some calculations with that. And then this third one, this is a really good one to kind of keep in mind, is to balance 1 element at a time, and that's what we did in the last one. We didn't try to balance 2 things at once. We focused on 1 element, and then by focusing on in that case, you focus on hydrogen. By focusing on the hydrogens, the chlorines kind of work themselves out later on. And then this is a good one to think about. Balance pure elements last. So if you ever have an element that's by itself, do that one last. So if we go back to the last equation, how we could have used that was, if I get our numbers back here again. So 1 carbon, 4 hydrogens, 2 chlorines, 1 carbon, 1 hydrogen, 5 chlorines. If you use that principle of balance pure elements last, chlorine is a pure element in our reactants. So that would be a good tip to say, hey, let's deal with chlorine last, not deal with that first. Why would that be so? Why would that be a tip to deal with pure elements last? Any thoughts on that? It's something you'll kind of, I think, intuitively figure out as you do these. Dorian?
There's other elements like the chlorine, kind of balance it out to the number of chlorines.
Exactly, yeah. You want to save that for last because you only have to deal with that by itself. Whereas if I try to balance the chlorines first, because over here in our products the chlorines put up the hydrogens, by changing the chlorine here, I also then change the hydrogen. So it makes it more complicated. It's easier to just deal with chlorines last because I have it where over here I can change my chlorine numbers without changing anything else. Okay, that's something I think you'll appreciate more as you keep doing some sample problems, but that's what they're trying to say there. Okay, a few other tips that I was able to find is, and this is just it's not even a tip, it's just a fact that on these, you adjust the coefficients, not the subscripts. Meaning, if you look at this sample reaction down here, which I'll write a little bit bigger up here. I know it's a little hard to see. Look at our sample reaction up here. Plus SO2. If we take count of everything, we have 1 zinc in our reactants, 1 sulfur in our reactants, and 2 oxygens. Products, you have 1 zinc, 1 sulfur, and what am I doing? And 3 oxygens. So this one, our issue is the oxygens. What they're saying is to balance the oxygens, this is what you cannot do. You can't just be like, oh, yeah, I'll just make that a 3. Because then what you're saying is, we're now using ozone in this reaction, not oxygen, right? Like you'd be changing the actual molecule. So if I want to balance, if I want to deal with my oxygens, I have to adjust the coefficient. The coefficient is the number in front. Okay. All right. And then the second bullet point, even, odd, multiply by 2 to make all even. So what they're saying is, if you look here, you have an even and you have an odd. So what they're saying is if you try and multiply everything by 2, so here, oxygen is even on the left and odd on the right, multiply by 2 to make your oxygen even. In other words, if I multiply my oxygen over here by 2, that will then, so if I put a 2, let me make this pair a little smaller. If I multiply zinc oxide by 2, what that will do for me is that will now give me 2 zincs and now 4 oxygens. And then I can come over here and I just have to multiply my oxygen by 2, and then we'll be all balanced. Well, actually, no, because we get 2 zincs. So then we have to multiply zinc by 2. These are at 2. So then I got to deal with my sulfur, so you multiply that by 2, which gives me 2 sulfurs, and now I have 6 oxygens. So then I got to deal with my oxygens. So then I would need to multiply this by 3 to get us to 6. I don't know if I went a little too fast there, but a little too fast. The idea is you got to just you have to keep adjusting the amounts until they get balanced. Another rule is balance the polyatomic ions as a whole. That one doesn't really apply here because there's no polyatomic ions, but I don't know, let's just keep doing some more example problems for you. So are we all good writing our down everything here? I'll let you finish writing this one, and I'll go a little bit slower on the next slide. So make sure you got everything written down here you need. As I said, I think this is a topic that requires a lot of you practicing. It's kind of hard to get it from just watching me do it as much. That makes sense. Are we good? So right? All right. So let's look at another one here. We have lead nitrate plus sodium chloride gives us sodium nitrate and lead chloride. So first, let's take account of everything. On our left-hand side, we have 1 lead. And what they're trying to say with balance the polyatomic ions as a whole is you don't need to break it up into counting nitrogens and oxygens. Just count it all as nitrate. So you have 2 nitrates in our reactants. And then Na, we have one of those. Chlorine, we have one of those. Then in our products, lead, you have one lead. Nitrates, you just have one nitrate. And then sodiums, you just have one sodium in your products and two chlorines in your reactants. Okay? So basically, we need to deal with our nitrates and we deal with our chlorines. I don't know that there's necessarily a best way to deal with them. I think let's try dealing with our nitrates here. Like, let's try putting a 2 there, and let's see what that does for us. So if we put a 2 there, let's update our numbers. That would mean there's 2 nitrates, and there's 2 sodiums. And again, you could have tried to deal with the chlorines first over here, and then go to your products. That's why I was saying that there isn't necessarily a right or wrong way to deal with these. We just got to just keep working with it. So you look back at our reactants, what would I need to do to figure this out? How would I get this balanced out? Huh?
45 sodium chloride.
Yeah, right, because if I put a 2 here, then, okay, that would get us balanced. Now you'd have 2 and 2. Okay. You could have gotten to this same place if you had started by adjusting something different than the nitrates. Okay. But again, the principle about this problem is like it'll make the problems quicker and easier if you keep the polyatomic ions listed as a whole. Because there's no need to break that up into smaller things. Okay. Questions about this one? All right. This is just it written out. All right. Now there's a kind of reaction called a combustion reaction. So you know something is a combustion reaction if you see basically a bunch of carbons and hydrogens combined with oxygen, and you make carbon dioxide and water. So when you're balancing these, I want you to think of CHO, CHO. Think CHO, meaning when you're doing a combustion reaction, balance the carbons first, then the hydrogens, then the oxygens. That's the simplest way to do these. And this is actually, like, if there's ever a rule to, like, make sure you remember, this would be a good one to really, really remember. It makes a big difference. Yeah, Dory? Oh, you can't see it? So, yeah. I don't think Orange Expo was ever meant to be written on the board. It's like, you ever thought about that? Like some of these Expo markers, you're like, maybe when it's like brand new orange, it's like it actually works for like a class period. Anyway, so let's use that principle to do this. So here we have 7 carbons in our reactants. We have 8 hydrogens and 2 oxygens. In our products, you have 1 carbon, 2 hydrogens, and 3 oxygens. So the CHO principle would say, all right, there's a lot going on here. Let's deal with our carbons first. So to deal with my carbon, to get my carbon to 7 in my products, I got to multiply carbon dioxide by 7. And when I do that, that'll then make this a 7. But then 7 times 2 would give me 14 plus 1. It would give me 15 oxygens. 15 oxygens in our products. Now again, principle of CHO says don't worry about the oxygens. Let's deal with the hydrogens, and then we'll deal with the oxygens last. So to get my hydrogens to balance out in my products, I need to multiply water by 4. Okay? And what that's going to do for me is that'll give me 8 hydrogens, which is what I want. But then now that'll update my oxygen numbers, which is why we wanted to deal with them last. Because now I'm going to have 7 times 2 is 14, plus another 4 is 16. 18. 18. 18. We have 18 oxygens here. So now we deal with our oxygens last. I need 8 oxygens in my reactants. So if I multiply my oxygen by 9, that will then get us to 18. So one of the other kind of principles I told you about was like deal with elements that are like by themselves, like the oxygen was by itself. Deal with that last. That's essentially why CHO is the kind of the order to go in. Whenever you're doing a combustion reaction, because you combine it with oxygen, which is just by itself, that's why you want to deal with oxygens last, because it gives you the ability to just throw that 9 in front of there to balance them out pretty quickly. Okay? All right. There you go. So I got 2 other ones up here. I think at this point I'm going to let you just start working on them. If you want to fill these in on your notes, I have the solutions worked out for you on the slide, but I want to make sure you got time to start working on the formative. But I'll leave these up here on the slide.